Well, I guess I'll start now. So since we haven't met since this past Thursday, let me begin by just giving you a brief recap of some of the things that we've done. So so throughout we always had D as a bounded domain in the complex plane. And we had the Dirichlet inner product. And this is just given by, for functions f and g, 1 over 2 pi times the integral of the dot product of the gradients of your two functions. And then we had this very important Hilbert space h of d. This is the Hilbert space completion of the compactly supported C infinity functions in D with respect to this inner product. And then the Gaussian free field, H on D, this is given by a random linear combination of basis elements of the Hilbert space. So the coefficients here are IID, normal 0, 1, and phi n. This is an orthonormal basis of the Hilbert space. And and we showed that if we have any function f in h of d, then the Dirichlet inner product of the Gaussian free field in f is well defined, and this is a normal random variable with mean 0 and variance given by the norm of the test function. And then what else did we do? So we also showed that if f is in h epsilon of d for epsilon positive, then we showed that we can make sense of the the L2 inner product of h with f, and this is going to be a normal random variable with mean 0 and variance given by what you get when you integrate your test function against the Green's function for the Laplacian on D. Oops, capital D. Yeah, and then we also established the Markov property for the Gaussian free field. And remember, what this said is that if you have U and D open, then you can write H as a sum, H1 plus H2, where H1, this is a harmonic on D, and on U, and H2 is a Gaussian free field on U. And then the last thing that we did is we established the conformal invariance of the Gaussian free field. And remember, what this said is that if, say, D1 and D2 are domains in the complex plane, for simplicity, we'll assume that they're bounded. And phi is a conformal transformation which goes from D1 to D2. And H is a Gaussian free field on D2. Then this implies that if you precompose H with phi, then you get a Gaussian free field on D1. Okay, so that's what we did in the last few times. What we're going to do today is we're going to look at a very useful but simple absolute continuity lemma for the Gaussian free field. And then after that, we're going to we're going to construct the circle average process. And then what's coming up later, we're going to do the SLE Gaussian free field coupling and also look at what are called local sets for the Gaussian free field. Okay, so that's the plan. So let me begin with this this absolute continuity fact for the GFF. So here's the statement of it. So we're going to assume that H is a Gaussian free field on D in the complex plane, which for simplicity we're going to assume is bounded. And we're going to suppose that we have a function f which is in H of D. Then it's true that the law of H plus f, this is mutually absolutely continuous with respect to the law of H, and the Radon-Nikodym derivative takes on a very simple form. And it's just given by a constant, a normalizing constant, times the exponential of the inner product of H with F. Okay? So this is what we want to prove. And if you look at this, you might recognize this. This is kind of like a version of the Gersanov theorem for the Gaussian free field. So it's sort of that flavor. And even though this is a very simple fact, and as we'll see in just a moment, the proof of this is very simple, this is actually something which is extremely useful when you work with the Gaussian free field. All right, so let's prove it. So let me start off with kind of a simple observation. So let's just recall that if x is a normal random variable with mean mu and sigma squared, then as everyone knows, the density of the law of x with respect to Lebesgue measure what is this? This is just 1 over the square root of 2 pi sigma times e to the minus x minus mu squared over 2 sigma squared. Okay, so everybody remembers that. And this you can rewrite. You just factorize this. This is the same thing as 1 over the square root of 2 pi sigma times e to the minus x squared over 2 sigma squared. That's the first term if I just compute the square here. And then I also have e to the minus mu squared over 2 sigma squared. And then the final term is just e to the x mu over sigma squared. And this first term here, this of course you'll recognize as being the density for normal 0 sigma squared. This term here, this is just a constant. And then we're left with this, this last term. And so what this tells us is the Radon-Nikodym derivative for the law of a normal random variable with mean mu and variance sigma squared with respect to the law of a normal with mean 0 and variance sigma squared. This is just given by a constant. This is equal to a constant times e to the x mu over sigma squared. Okay, so this is kind of an elementary fact about the Gaussian distribution, and now we're going to use this to derive this proposition. Okay, so this tells us that if we write H, our Gaussian free field, as the sum of alpha n times phi n, where as usual the alpha n's are IAD normal 0, 1, and our phi n's, these are an orthonormal basis of h of d, then if we weight the law, of h by the factor given by e to the h inner product with f times a normalizing constant, then if I assume that my f has the following series expansion, let's say bn phi n, this is my f and h of d, then this factor here I can rewrite as a constant times e to the sum over alpha n bn. And so just applying the fact that we just looked at above, we see that that this has the effect of shifting the mean of each alpha I by bi, and this is the same thing. Yeah, and this is the same thing as this is equivalent to as just adding f to h. Okay, so this is a very simple and kind of basic fact for the Gaussian free field, but it's very, very useful. Let me just mention one simple consequence of this. Here's one useful consequence. And that's that if H is a Gaussian free field on a domain D, and I have open sets U and V, which are nested in D. So so here U and V are open, and I'm also going to assume that the distance between V and the boundary of U is positive. Okay. Then, by the Markov property, I know that the conditional law of the Gaussian free field, H restricted to V, given its values on the complement of U in D, this can be written as the sum of a Gaussian free field on U and restricted to V plus a harmonic function which is harmonic on V. And so if you just apply the proposition because this function is harmonic, so it's smooth, we see that the law of h restricted to v, this is going to be mutually absolutely continuous with respect to the law of a Gaussian free field on U restricted to V. And this is very useful because this in turn implies that any almost sure property of the latter has to hold for the former. So holds almost surely for the former. Okay. So yeah, so this absolute continuity fact, it might seem like this is a very simple thing, and it is a very simple thing, but this is in particular really, really useful when you work with SLE in the Gaussian free field, because you can kind of perform a change of boundary conditions, and this sort of changes the SLE, which is coupled with the Gaussian free field that we'll see soon, and this allows you to sort of transfer properties between different types of SLEs. Okay, so that's the first thing I wanted to do quickly. Now what we're going to do is we're going to look at the circle average process for the Gaussian free field. Okay. All right, so the first thing that I want to do is just remind you that if we have a function f, a test function, which is, say, compactly supported in C infinity and D, then we have that we can define the L2 inner product of h with our function to just be minus 2 pi times the Dirichlet inner product of h with the inverse Laplacian of f. Okay. And in order for this to make sense, at least off of a set of measure 0, which depends on f, this makes sense whenever this function f has the property that its inverse Laplacian is in h of d. Okay. And this can be the case very generally. In particular, this can be the case even if this f here, let me put this in quotes, if this is a sufficiently nice measure. So let's do an example. So as an example, a very important example, and the one we're going to focus on now, is let's suppose that we have a point in our domain and epsilon positive. Then what I'm going to do is I'm going to let rho sub epsilon z, this is going to be the uniform measure on the boundary of the ball centered at z of radius epsilon. Okay, so this is a measure we can look at. Oh, I should mention before I go further, by the way, that the treatment that I'm giving for the circle average process, this is based very closely on, if you want to reference, this is based on section 3 of this paper by Duplantier and Sheffield. on Liouville quantum gravity and KPZ. So this is the paper Liouville quantum gravity and KPZ. Okay, so rho epsilon z is going to be the uniform measure on the boundary of our ball with radius epsilon. And then what we can do is that we can just define h subscript epsilon of z. So this is going to be the average of our Gaussian free field on the boundary of the ball centered at z of radius epsilon. And the way that we define this is that this is going to be the L2 inner product of the Gaussian free field with this measure, which in turn is defined by taking the Dirichlet inner product times minus 2 pi of the Gaussian free field with the inverse Laplacian of this measure. Okay. And again, for this to be defined, remember what we have to check. We need to show that that this thing here, this inverse Laplacian, actually needs to be an element of h of d. And it turns out that this is not so hard to show because you can write down what the inverse Laplacian is explicitly. It's just given by inverse Laplacian of this measure. I'm going to call this psi sub epsilon of z. This is you can just calculate this, and it's equal to minus the log of the maximum of epsilon and the distance between z and y minus a function which will give this 0 boundary values. So we're going to call this correction g tilde sub z epsilon, where here this g tilde, this is just the harmonic extension of this function here, so minus log of epsilon, sorry, minus the log of the maximum of epsilon and the distance between z minus y from the boundary of the domain to the interior of the domain. And this here is viewed as a function of y. Okay. So one can check directly that it's just basically a calculus exercise to show that the inverse Laplacian of this measure here is just given by this function. And once you have this explicit form, you can then show that, again, another calculus exercise, that this function here lies in h of d, and so it makes sense to write down this definition of the circle average of the Gaussian free field. All right, and so what do we have at this point? So what we know up until now, so what do we know? So at this point, we know that for each z and d and epsilon positive, we have that this h epsilon z that we defined above. This makes sense. We know how this is supposed to be defined. But the kind of tricky thing here is that since the uniform measure on the boundary of a ball of radius epsilon, this is not in h of s for any positive s, because it's in fact not even an L2 function. It's not even an L2 function. We can't use what we did before to get that this is going to be defined simultaneously for all epsilons and z's. So so we do not know. So we don't know kind of a priori, or we don't have a priori that the map, which goes from an epsilon z pair to h epsilon z, is defined for all epsilon z pairs simultaneously. Off of a common set of measure 0. Okay, so we don't get that for free from our construction of the Gaussian free field as a distribution value random variable from earlier. All right, so what are we going to do then? We're going to do kind of the standard thing one does for Gaussian processes like this to construct it, similar to the way that you construct Brownian motion. And yeah, so what do we do? We're first going to identify the covariance function for our Gaussian process. And then once we've done that, we're going to use the Kolmogorov-Chentsov theorem to show that this process has an almost surely locally Holder modification. And once we've done that, then we'll have a way of defining or making sense of the average of the Gaussian free field on any circle of radius epsilon simultaneously. Okay, and so how does this go? So let's first do the covariance function. Let's just do the calculation. So what do we have? Well, we have that the covariance of the average of h on the circle of radius epsilon 1 centered at z1 with the average of h on the circle centered at z2 of radius epsilon 2. So here epsilon 1, epsilon 2 are positive, and z1 and z2, these are in our domain. So let's just calculate this covariance. And the first step is just to write down what the definition of these two things are. And the first one, remember, is the same thing as the Dirichlet inner product of h with minus 2 pi times the inverse Laplacian of this measure. And the second one we can write similarly as the Dirichlet inner product of H with minus 2 pi times the inverse Laplacian of the uniform measure on the second circle, like that. Okay, and whenever we have the Gaussian free field, and we take the Dirichlet inner product of it with respect to two functions, then the covariance is always just given by the Dirichlet inner product of the two functions you're looking at. So you just take the Dirichlet inner product of these guys. So you have inverse Laplacian of rho epsilon 1 z1 with inverse Laplacian of rho epsilon 2 z2. You have that Dirichlet inner product. And once you've got it to this point, you do the same thing that we did repeatedly before, and that's that you perform an integration by parts to kill one of these Laplacians. So this you can write as minus 2 pi times, say, the inverse Laplacian of rho epsilon 1 z1 integrated against, in the L2 sense, rho epsilon 2 z2. You take this this Dirichlet inner product here. Sorry, this L2 inner product. And then recalling that, remember the Green's function, g of xy, remember that this satisfies the property that its Laplacian is equal to minus 2 pi times the delta function at y, evaluated at x. And so using this, we can write down an explicit formula for that L2 inner product there. Okay, and what is it? It's just given by the integral of the Green's function against these two measures. Okay, and this is now a very nice and concrete thing, because this is just the Green's function for the Laplacian averaged on these two, the boundaries of these two balls. And I'm going to call this this function here g sub epsilon 1 epsilon 2 of z1 z2. Okay, so we just finished the first step. So we identified what the covariance function is for this Gaussian process. And now what I'm going to do is state the result that you get after you plug this into the Kolmogorov-Sentsov theorem. So the proposition says that for any eta which is less than 1/2, the process that you get from averaging the Gaussian free field on circles of radius epsilon, this has a modification which is locally eta Holder continuous in z and epsilon. And just to remind you what that means, in this case, this means that for each compact set K, so for each K and D compact, and we're going and epsilon positive, epsilon sub 0 positive, there exists a constant m actually, let me not call it a constant. There exists m positive, which is random. such that if you have 2 points in K, so Z1 and Z2 are in K, and epsilon 1, epsilon 2 are bigger than this lower bound epsilon 0, then the difference between h epsilon 1 of Z1 and h epsilon 2 of Z2 is at most this constant m times the distance between Z1 and Z2 plus the distance between epsilon 1 and epsilon 2 to the 8th power. Okay? So that's what it means for this to be locally Holder continuous. And one thing that I want to point out is that you see this this half here, and if you remember, regular Brownian motion is always Holder continuous with any exponent less than 1/2. And so the modulus of continuity that we're going, well, the bound for the modulus of continuity that we're going to get for the circle average process here, when we prove this proposition, is analogous to what you get when you prove the continuity of Brownian motion in the same way. You see exactly the same Holder exponent. Yeah, and the proof of this, it just has 2 steps that we're going to go through. The first one is the following lemma. And what it says is that if you have a subset of your domain D, which is compact, and you have an epsilon sub 0 which is positive, then there exists a constant, this time it's not random, m positive, such that the variance of the Gaussian free field evaluated or averaged on the circle centered at Z1 of radius epsilon 1 minus the average of the Gaussian free field on the circle of radius Z2, epsilon 2 centered at Z2. This is going to be less than or equal to m times the distance between Z1 and Z2 plus the distance between epsilon and epsilon 2. And here, just to emphasize, this is for all Z1 and Z2 in K, and epsilon 1, epsilon 2 bigger than epsilon 0. Okay? So the first step in the proof of the continuity is just to get a bound on the modulus of continuity of the variance. Variance of the difference of these circle averages. All right, and how do you show this? So you just have to compute. So you look at the variance of h epsilon 1 of Z1 minus h epsilon 2 of Z2. And let's just expand this. So this I can write as the variance of the first term, h epsilon 1 of Z1, plus the variance of the second one, h epsilon 2 of Z2, minus 2 times the covariance of h epsilon 1 of Z1 and h epsilon 2 of Z2. Okay, so we just took the variance and then expanded it. And in this first one here, this is what we called G epsilon 1 of Z1 from before. And the second variance is just G epsilon 2 Z2. And then the last term is 2 times G epsilon 1 2 Z1 Z2. Okay. And in this you can rewrite as, a little bit more suggestively as g epsilon 1 of z1, z1. I'm going to take one of these two factors, one of these two terms here, and pair it with the first term. So I have g epsilon 1, epsilon 2 of z1, z2. And then I can pair together the other two terms. I get g epsilon 2 of z2, z2. Ooh, this might be hard to read. Let me write this over here. Okay, let me go to this side. Yeah, so this last term here is just, let me write it again. So it's g epsilon 1 of z1, z1 minus g epsilon 1, epsilon 2 of z1, z2 plus g epsilon 2 of z2, z2 minus g epsilon 1, epsilon 2 of z1, z2. Okay, so this is what this, this variance is equal to. And so what you see is that in order to finish, you just need to show that all that you have to do is you need to show that the map, which associates a quadruple, epsilon 1, epsilon 2, z1, z2, to g epsilon 1, epsilon 2, z1, z2. You just need to show that this map, this is Lipschitz. Is a Lipschitz function for z1 and z2 in K, and epsilon 1, epsilon 2 greater than or equal to epsilon 0. But the point is that this function g here, this was defined explicitly in terms of the Green's function right over here. So this is a very explicit thing, and so this is a calculation that you can just do. So this is something that you can just see by hand. So this this can be checked using the explicit formulas for everything. Okay, so I don't want to do this because this is not hard. It's a little bit tedious, but it's not a difficult thing. And now what I'm going to do is I'm going to use this to finish the proof that that the circle average process has a Holder continuous modification. So here's the proof of the continuity proposition. All right, so the trick is that if I take any epsilon 1, if I have any epsilon 1 z1 and epsilon 2 z2, and look at the difference of these two random variables, this is going to be Gaussian. What do we have? We have that for each integer n, there is a constant, say c sub n, such that if you look at the 2nth moment of the difference of h epsilon 1 z1 minus h epsilon 2 of z2, then this is just going to be equal to Cn times the variance of the difference of these two circle averages. to the nth power. Okay. And if you take n large enough here, then you can apply the Kolmogorov-Chentsov theorem. So the Kolmogorov-Chentsov theorem then implies that this h epsilon of z, this has an eta locally Holder continuous modification whenever eta is in an interval from 0 to n minus d divided by 2n. And here, what is d equal to? D is going to be equal to 1. This is from the epsilon variable, plus 2. This is from the spatial variable. And so the whole thing is just equal to 3. Okay. So this is what you get when you apply Kolmogorov-Chentsov. And then if you send n to infinity, you can make this as large. You can make this as close to a half as you would want. So if you send n to infinity, you get the proposition. Okay, and this is the end of the construction of the circle average process for the Gaussian free field. Now, one thing that I want to mention is that there are many different ways to take the Gaussian free field and to regularize it so that you actually get something which is a function. The circle average process is actually very convenient because circle averages, of course, play very well with harmonic functions, because harmonic functions are characterized by the property that if you average them over any circle, then what you get is just the value of the harmonic function at the center of the circle. And so these circle averages are very convenient to look at, for example, when you do things with the Markov property in the Gaussian free field. In particular, when you work with Gaussian free field local sets. And we'll see that coming back a little bit later. All right, and now in the last few minutes, what I want to do is just explain one connection between the Gaussian free field and Brownian motion. So here's the statement. So what it says is that if you fix a point z in your domain and you let t sub 0, this is going to be the smallest t, such that the ball centered at z of radius e to the minus t is contained in your domain. And then what I'm going to do is I'm going to let b sub t, this is just going to be equal to the average of the Gaussian free field on the circle of radius e to the minus t0, minus its average on the same circle of radius t0 centered at z. Okay, so what I'm doing here is I have my domain, and here's D. I have a point z here. This is the ball of radius e to the minus t0 centered at z. And I'm looking at the average, the difference between the average of the Gaussian free field on this circle and a smaller circle, like that. And this process I'm calling b sub t, and the statement is that this b sub t is this is just a standard Brownian motion. Okay, so when you take the Gaussian free field and you average it on concentric circles, then the resulting process is just Brownian motion. And this is also an extremely convenient fact. And the way that it's proved is that, I mean, first of all, you know that B sub t, this is just a Gaussian process. It's even a continuous Gaussian process. And so all that you need to do is you just need to check that this process has the same covariance function as Brownian motion. Okay, so this is something that you can just check. And I also don't want to carry out the calculation of this, but you can see that this is the case by using the explicit formula for, this is a nice exercise actually for someone to think about, the explicit formula for the covariance function. So I'll leave this as an exercise. Okay. Okay, so the last thing that I want to do in the last few minutes before lunch is just record one remark. About the circle average process, and that's that if you take your value of epsilon here to be 1 over n, or say n is an integer, then h epsilon of z, this process is in some sense, it's very close, or it's very well approximated by, to the discrete Gaussian free field on your domain intersected with, say, the square lattice. Okay, so these two processes are very, very similar. And this is something that you can also check by using, for example, the local center limit theorem to estimate or to compare the covariance function functions for these two Gaussian processes. So it's kind of a meta statement. Things that are true about the discrete Gaussian free field on this kind of a graph approximation for your domain are, should be true for the continuum Gaussian free field when you consider its circle averages on circles of radius 1 over n and vice versa. Although it's not really a theorem, so one has to, you have to do some work. In some cases, to try to transfer statements back and forth. But at least qualitatively, these are two very similar things. And okay, so that was the last thing that I wanted to do. So I'll stop there. Are there any quick questions before lunch?